Good morning all. In this session, the generation of three-phase AC voltage is discussed. A three-phase supply is a set of three alternating quantities displaced from each other by an angle of 120 degrees. Here you can see three sinusoidal waveforms are shown. Phase 1, phase 2 and phase 3. Here you can see that the second phase or the phase 2, this red trace is lagging with respect to the reference wave. Here phase 1 is taken as the reference. So here you can see that the phase 2 is lagging with respect to phase 1 by an angle of 120 degree. And the phase 3, you can see that it is lagging with respect to the phase 2 by 120 degree, but it is lagging with respect to phase 1 by 240 degrees. So a three-phase set consists of three alternating voltages which are displaced by 120 degree each. So if you express or if you represent those waveforms in equation form, if you take this phase 1 as reference, any phase can be taken as reference. So here we are taking this voltage as reference. So it can be represented as EA is equal to EM sin omega t, where EM is the amplitude of the waveform. And in case of a balanced system, the amplitude of all the three waveforms will be same. So first waveform can be represented as EA is equal to EM sin omega t. And the second waveform, here the red trace, here you can see that it is lagging with respect to the first trace by 120 degrees. So it can be expressed as EM sin omega t minus 120 degree. The amplitude of all three waveforms are same and it is taken to be EM. And the third one, EC, here you can see that it is lagging with respect to the first waveform by 240 degrees. So it can be expressed as EC is equal to EM sin omega t minus 240 degrees. And you can see that minus 240 is equivalent to plus 120 degrees because the whole circle is 360 degrees. So minus 240 is plus 120. So EC can be expressed as EM sin omega t minus 240 degree or it can be expressed as EM sin omega t plus 120 degree. Now if you add the instantaneous value of these three voltages, that means these expressions, if you add EM sin omega t plus EM sin omega t minus 120 degree plus EM sin omega t plus 120 degree, we will get it as equal to 0. Graphically you can see it from here. The instantaneous value of the phase 1 is 0 and at this point instantaneous value of the phase 3 is this positive quantity and instantaneous value of phase 2 is this negative quantity, and this magnitude and this magnitude are same. That means at any instant, if you sum up the instantaneous value of these three voltages, you get it as 0. That means EA plus EB plus EC is equal to 0. That is the sum of the three phase voltages at any instant is equal to 0. Necessity and advantages of three-phase system. Even though the three-phase system is a little bit complicated compared with the single-phase system, the three-phase system of voltages has its own advantages in terms of the generation, transmission and utilization. These are some of the major advantages of the three-phase system. And the first and the foremost is to transmit the same amount of power over a fixed distance at a given voltage. The three-phase system requires less amount of copper than is required by a single-phase system. That means if we compare the copper requirement for the transmission of a given amount of power over a given distance, in three-phase system requires less amount of copper than is required by the single-phase system. And less amount of copper means all other accessories like other infrastructure requirements will also be less. And secondly, for the same rating, three-phase machines are smaller, simpler in construction and have better operating characteristics than single-phase system. And polyphase motors have a uniform torque, where most of the single-phase motors have a pulsating torque. And the voltage regulation of a three-phase transmission line is better than that of single-phase line. That means the voltage regulation means the different change in terminal voltage from no load to full load. Regulation is better means this voltage change from full load to no load will be lesser compared with the single-phase transmission system. These are some of the major advantages to be listed, but a number of advantages are there in going for three-phase system than a single-phase system. Generation of three-phase voltages. Three-phase voltages are often produced with a three-phase AC generator, whose cross-section is shown in figure. A generator basically consists of a rotating magnet called rotor, which is surrounded by a stationary winding called stator, and these three separate coils will be there on the stator. Generation of three-phase voltages. The three-phase voltages are often produced with three-phase AC generators known as alternators. It consists of a rotating magnetic field, generally known as termed as the rotor, and a stationary winding, generally termed as stator. Three separate set of coils will be there on the stator. Here in this figure you can see that A constitute one coil, B constitute another coil, and C constitute another coil, and each of these coils are displaced by 120 degree from each other. That means B is displaced by 120 degree with respect to A and C is displaced by 120 degree with respect to B and same C coil is displaced by 240 degree from the coil A. Now if this magnetic field is rotated with an angular velocity omega, as in the case of a single phase generator, a voltage will be induced on each of these coils. That means a voltage will be induced across each coil A B and C. And as these coils are displaced by 120 degree each, there will be a phase difference of 120 degree each from the voltage generated in each coil. That means the voltage generated on the coil B will be displaced by 120 degree from that of the A and the voltage generated on C will be displaced by 120 degree from the voltage generated on the B and the same voltage on the C will be displaced by 240 degrees from the voltage generated on the A and each of these coil can be considered as a single phase generator, and each of the variation of the voltage induced on each coil will be sinusoidal. And in this figure you can see that one similar points, say the starting ends or the finishing ends of the coil A B and C are connected together and is termed as N. Here you can see that either the finishing end of coil A, B and C or the starting end of the coils A, B, C are connected together and is taken as a common point, and the voltage will be measured between the points A, B and C with respect to this point N. So the potential of the voltage of the point A will be measured with respect to N. Similarly, voltage of B will be measured with respect to N. Potential of C will be measured with respect to N. Now if you see the variation of the waveforms on each of these coils, if you consider or if you take the first coil as a reference, here you can see that the variation of the voltage on the first coil will be like this, and as the second coil here B1 B2 is displaced by 120 degree, the variation will be like this. That means the similar points on the waveform will be lagging, or it will be displaced by 120 degree from that of R and B. Similarly, the variation on the green, there will be a phase difference of 240 degree between the first waveform and the third waveform, and between the second waveform and the third waveform a phase difference of 120 degree will be there. And here you can see that this dotted waveform represent the voltages generated in the previous cycle, and this is a complete variation of the cycles. If the rotor is rotated continuously with an angular velocity omega, a continuous waveform like this will be obtained. Since as the physical parameters of the coil, length, breadth and all other parameters are same, the amplitude of the generated voltage on each coil will be similar, and the maximum value of each coil will be, or the maximum value of the voltage generated on each coil will be same. Now let us see how a three-phase voltage can be represented in a phasor diagram. As we have seen from the previous slide, one end of each of the three coils are connected together and is taken as a common point. And based on that, the potential of the other point, as shown in the figure, here you can see in this diagram, the potential of the, because we have interconnected the similar points, or either the finishing ends or the starting ends of the coils A, B, C together, and that will be considered as the common point, and the voltages will be measured with respect to this common point and the other point. So if you measure those voltages for the first phase, if you consider the first phase or the R phase as a reference, it can be represented as VIN is equal to VP angle 0, as we have seen in the discussion of the representation of sinusoidal waveform in phasor form. So, and you can see that as we have seen that the voltage on the second coil will be lagging with respect to the first coil by an angle of 120 degree. So that phasor can be represented as VBN is equal to VP angle minus 120 degree. From here you can see that there is the second waveform is lagging with respect to the reference or the first waveform by 120 degrees, and that is represented here. You are considering this as the reference direction, and VAN is drawn, or the R phase is drawn like this, either red phase or A phase. Sometimes we will be using RYB notation or ABC notation. And the second phase, either the yellow phase or the B phase, here you can see that it is lagging with respect to the R phase by an angle of 120 degree. So this angle is 120 degree and it is measured in the clockwise direction. And from this diagram you can see that, from this expression you can see that the third voltage VCN is lagging with respect to the reference by an angle of minus 240 degree. That means 240 degrees will be measured in this direction, and this is the position, and the phasor diagram, the magnitude of the voltages or the amplitudes are same, so this length will be the same as this length, and this angle will be minus 240 degrees. And the same you can see that minus 240 is the same as plus 120 degree. The three-phase voltage as VN is equal to VP angle 0, VBN is equal to VP angle minus 120 degree, and VCN is equal to VP angle minus 240 degree or VP angle plus 120 degree. And as these amplitudes are same, such a set of three-phase voltage is said to be a balanced three-phase voltage. Amplitude of the three waveforms are same, but they are displaced by 120 degree and 240 degrees successively from the first phase. The phase sequence in a three-phase system is the time order in which the voltages pass through their respective maximum values. The phase sequence is important in the operation of especially induction motors. If the phase sequence is reversed, the direction of the rotation of the three-phase motors will be reversed. Here, the phase sequence in three-phase system. The phase sequence in a three-phase system is the time order in which the voltages pass through their respective maximum values. That means if you consider the A phase as a reference, once the A phase has passed through its maximum point, next we have to check which phase is passing through its maximum. If the rotor is rotated in the anti-clockwise direction and the coils are disposed as shown in this figure. Here you can see that if it is rotated, after A phase, B phase will be coming, and after 120 degree, C phase will be coming. That means if this is the starting end of the coil A, this is the starting end of the coil, and if the magnet is rotated in this direction, after A has passed through its maximum value, the voltage on the waveform, voltage on the B will be passing through its maximum value. Then only C will be coming. That means the voltage waveforms will be passing through their maximum values in the order A, B, C. And such a system is known as the ABC sequence. But if the rotor is rotated in the clockwise direction, or if the direction of the rotation of the magnetic field is reversed, you can see that after A, C will be coming. That means after A has passed through its maximum value, C will be attaining its maximum value, then only B will be attaining its maximum value. In that case, the sequence is said to be ACB. Generally, the ABC sequence is considered as positive. The anti-clockwise direction is considered to be positive. So, if ABC sequence is followed, in that case, you can represent the phasor diagram like this. That means if you are taking VAN as reference, this will be the reference direction. So, after the A phase, B phase will be coming. That means if you traverse in the clockwise direction, actually these phasors are rotating in the anti-clockwise direction from the convention of the phasor diagram. So once this has or if these phasors are rotating in the anti-clockwise direction, after R phase, B phase is coming, then only C phase is coming, and B phase is lagging with respect to A phase by 120 degree, and C phase is lagging with respect to A phase by 240 degrees. But if the direction of rotation is changed, say if it is rotated in the negative sequence, you can see that after A, C will be coming, and after C, B will be coming. That we have already seen. If the direction of rotation of the generator or the magnetic field is reversed, after A, C will be attaining its maximum value, and then only B. That means in the phasor diagram concept, it will be, these phasors will be rotating in the anti-clockwise direction, and here you can see that once AN has attained its maximum value, then C will be attaining its maximum value, then only B will be attaining its maximum value. In that case, it is said to be negative sequence. So in case of a positive sequence, the phasor representation of the voltages will be VAN is equal to VP angle 0 degree, then comes VBN with VP angle minus 120 degree, and VC is equal to VP angle minus 240 degree if positive sequence or ABC sequence is considered. And in case of negative sequence, that is ACB sequence, in that case VAN, if you are taking VAN as reference, it will be represented as VP angle 0. Then instead of VBN, VCN will be coming there, and VCN is equal to VP angle 240. It is the same as VP angle minus 120 degree, and VBN will be VP angle plus 120 degree. Here you can see that VP angle 240, this is 240 degree, means this is minus 120 degree. Both are same. As we have seen earlier, the instantaneous value of a three-phase balanced system will be equal to 0. And here you can see that we have represented the A phase as VAN as VP angle 0, VBN as VP angle minus 120 degree, and VCN as VP angle plus 120 degree. And VP angle 0 can be written as VP into 1 plus J0 using this relation. If a complex quantity is represented as x plus jy, x is the real part and y is the imaginary part, and if it is represented as polar form, it will be r angle phi. In that case, x will be given by, or x is equal to r cos phi and y is equal to r sin phi. If you use this relation, here you can get this can be simplified as Vp can be taken out, and here you get cos 0 plus j sin 0 plus cos minus 120 degree plus j sin minus 120 degree plus cos 120 degree plus j cos plus 120 degree. So you get this relation, and here you can see that it is equal to 0. At any instant, the sum of the voltages of the three phases will be equal to 0. And from the phasor diagram also, you can get that if you find the resultant of these two vectors, the resultant of these two vectors will be somewhere here. That means resultant of R phase and B phase will be obtained by completing the parallelogram, and here will be the resultant in this direction. And you can see that it is directly opposite to the direction of the yellow phase. That means instantaneously at any instant, the sum of the voltages on three phases will be equal to 0. Thank you for watching.